So we're going to start off on chapter 2 then. And chapter 2, if you've been looking ahead, deals with the study of kinematics, specifically in 1D, one dimension. All right, so you kinesiology majors, what is kinematics? All right, so kinematics is the study of motion. And so that's what we're going to focus on. And we're going to start off studying in one dimension, or 1D for short. And that means that we only consider one direction of motion. In other words, something like up and down, left and right, north, south, etc., etc., etc. All right. I know up and down sounds like two directions, but it's only one direction in a line. Okay, so that's what I mean. We're only going to deal with one direction. Now, of course, that wouldn't be fun to just do one dimension. Eventually, we get onto two dimensions, but we'll start off with a simple case in one dimension, and we'll work up from there. All right. Kinematics deals with. Oh, you got to get over there. Kinematics deals with really three quantities. In general. All right, and those three quantities, you've met one of them, or you mentioned a couple of them actually. So velocity, acceleration are the two that you've already mentioned to me. And the third one is displacement. And all three of those quantities are vectors. All right, so velocity, acceleration, and displacement are vectors. We're going to start off, I'm going to take it slow, we're going to just introduce all three of those quantities and talk about how the equations that we could use to solve for those things. All right, so let's start off at the bottom of the ladder, and that's displacement. All right, somebody give me a definition for displacement. What do you think of when I say displacement? Yeah. All right, good. It is exactly that. I'm going to preface that with the vector difference. Ooh, that's much worse. Between two positions. All right, so the vector difference between two positions. Now, in that way, a lot of times people sort of interchange displacement and position. But position is generally a little bit more basic. All right? In order to have a displacement, we need to define a position. All right? And then we need to take the difference between those two positions. So, for example, I could draw something like this. So here's a starting point. Say you're walking from the start to the end of something. I don't know. You're just following a path. You can define the start and the end. Now you could walk there any number of ways, right? You could take some sort of strange, circuitous route like so, whoop, and get to the end, right? Or you could walk in a straight line, which we'll say that's straight, all right? The displacement is specifically the straight line, right? So the displacement is the difference between 2 points, and the key word here is vector. The vector difference between the end and the start is just a straight line between those 2 points. So this straight line represents the displacement. And I'm going to write that like so, delta x, with a little vector symbol on top of it. All right, that's the symbol that generally I'm going to use for displacement. Now x is just sort of a random letter. That's a common letter to use, but I could just have easily written delta y or delta z or delta r, whatever I want to write. But in general, whenever you see delta lowercase letter that isn't reserved for some other physical quantity, that's how we label displacement. All right. Now, displacement is not the same thing as distance. All right. As you can sort of get, a feel for by looking at this graph. All right. I've drawn two different lines here, and you can say, you can calculate a distance traveled in either case. All right. In either case, the distance is different, but only one thing represents the displacement, and that's that straight line, that straightish line, that line that should be straight. All right. So as a more concrete example, then let's take a look at somebody doing a running race. So I'm gonna give you two options here. I'm gonna change colors because I'm sick of red. So two different runner doing two different races. I'm gonna calculate, or I'm gonna write down the distance traveled. And I'm going to write down the displacement, which is delta x in our physics world so far. All right, so in one race, we have the 100-meter dash. All right, the 100-meter dash, who's in track here? Anybody did track in high school? All right, the 100-meter dash is what, a straight line, curved? Straight. Yeah, it's straight. So in the 100-meter dash, you travel at a distance of, wait for it, 100 meters. All right, and your displacement in the 100-meter dash is also 100 meters. All right, in that example, the straight line is the same as the curvy line. Well, the curvy line's straight. All right, so that's a very, very simple example where the distance and the displacement is exactly the same. Another type of run you might have done as a track and fielder is the 1600, which is the mile, which is 4 laps around the track. In that case, the distance traveled, well, it's 1600 meters, unless you cheated. All right, but what's the displacement?
0.
All right, 0. That's exactly right. All right, because remember, the displacement only cares about the position of the start and the position of the end and how they're related to each other. And the 1600, you do four laps around the track. You start and end in the same place. Your displacement is 0. All right, the distance is just the distance you traveled. Yeah. I'm sorry, is the work? The work done? No. Work is a different concept. We'll come back to that in a week or two. Yeah. It is not the same as the work done. All right? All right. So that's the difference between displacement and distance. And again, like all things we do in this class, make sure it's clear now, and that'll make it easier when you're dealing with it in actual real-life physics problems. All right. Now I want to give you a little bit, something a little bit more, an example that's a little bit more tricky. All right, so let's take a look at one more example. And this one is going to be, I'm going to try something here. Let's try this. All right, because I can type faster than I can write on this thing. How do I make the font bigger? Does that work? No, it doesn't work. Font, 12 point. Let's go 18. All right, so you go for a run. Whatever I just hit is bad. Don't hit that. You go for a run. And so let's give you so you start off and you head north. What am I typing? Hitting my touchpad. All right, first you head north for a mile. So first you head north for a mile, then east for 0.75 miles, and then you end up heading south for 0.25 miles. So I want to know what is your displacement? All right? I like that much better. Oh, I'm not going to get out of here. All right, so that's the question. Now I want to know what's the actual displacement. Well, if I add all these things together, I could come up with the distance. All right? The total distance traveled, 0.75, 0.25, that's 1, and then, we had one more. So the total distance traveled is 2 miles. But I guarantee you that the displacement's not going to be the same. All right, we need to figure out what that displacement is. So if I draw a little bit of picture here, a little bit of a picture. So here I start off, and then I go north. That's not what I wanted. I go north. What are you doing? I don't remember the keyboard shortcut for the, do I? There it is. All right, so you go north for 1 mile. North, let's go straight north. All right, then you go, it's going to be white. Third time's a charm. Sorry, give me a second to work out the kinks. I have no idea what color I am. That shouldn't be black. There we go. Thank you. All right, now go away. All right, so you go north for 1 mile, then you head east for 0.75 miles. So I'll try to be kind of roughly to scale here. And then we go south for a 1/4 mile, like so. All right, so my displacement then is the vector difference between this point right here and the start point right here. In other words, if I draw that, so if I draw it, my vector displacement is represented by that red line. All right, so this is what we're after. We're after delta x. Okay? It's certainly not the same thing as 2 miles, the total distance traveled. So the question is, how do we figure out what that displacement is? Right? Anybody, so who's done this before? So how do I figure that out? All right, sort of using right triangles. That's the right idea. Because of the way that these lines are oriented, it would be a little bit tricky to do that. Before I'll inevitably have to use a right triangle if I want to. I will have to use a right triangle, but before I can do that, I have to do something else. All right, I think what you're thinking of is because each of these legs of the race or the run are vectors, I'd have to break those vectors up into their components. Again, we'll come back to that in a little bit more detail, but these are already, they're already perpendicular, so I don't have to do anything too tricky here. But what I can't do, I can't just add the legs where I'm going north-south to the legs where I'm going north and east, right? Or I'm sorry, east and west. I need to break those up. I need to treat them differently. So what I'm going to do is I'm going to make a little table here, and I'm going to add up each component in its own column. So I'm going to add up how far I've gone north and how far I've gone east. All right. So for leg 1, I've gone north 1 mile. In that leg, I didn't go east at all. All right. In leg 2, I go east for 0.75 miles, but I don't go north at all. All right. And then finally, in leg 3, I go south for 0.25 miles, and I don't go east at all. Now, I've written 0.25 miles here, but that's not completely right, because we're adding vectors here. So what do I need to include in this 0.25? A negative sign. And you can see it in this picture here. If I just added it, that would sort of make me think that this line should be drawn up here. But no, it's going the other way. All right? So what I'm basically doing here is vector addition, although I'm trying to be a little bit discreet about it. And so what I get then is a solution where the total distance north that I've traveled is 0.75 miles. The total distance east that I've traveled is also, coincidentally, 0.75 miles. And the result of what I've done is I've basically calculated a vector delta x, my vector displacement, and I can write this a couple different ways. One of the ways that I can write it is like this. All right, this is a vector as I've written it, where this first number represents how far I've gone north. The second one represents how far I've gone east. All right. Or what I can do is figure out, okay, what I really want to know is the total magnitude, the total length of this vector, and the direction of that vector. And because I haven't drawn it, I'm kind of at liberty to pick what direction I'm after. So let's just say that I'm after this direction, theta. All right? Theta is actually really easy in this problem. Does anybody know what theta is off the top of your head? How would I calculate what theta is? All right, so somebody back there said it already. I need to break this guy up into a right triangle. So now is when I come into the right triangle. So here's my right triangle. Sorry for my not straight lines. I need to practice that. All right. What's the length of each sides of these right triangle of the right triangle? 0.75. Right. So this is 0.75 north. This is 0.75 east. In order to find theta, I take the inverse tangent of the opposite over the adjacent, like we just talked about. The inverse tangent of 1, if you remember, is just 45 degrees. Okay? So I got this because tangent of -1, the inverse tangent of 1 is 45 degrees. All right? Now I need to find, in addition to this angle then, I need to find the magnitude of my vector. All right? My magnitude of my vector is the length of the hypotenuse of this triangle. So using Pythagorean's theorem, I can find the magnitude of delta x, which is written like this. I put these two bars around the outside of my vector. That says the magnitude. That says ignoring the direction. The magnitude of my vector is going to be equal to the square root of 0.75 squared plus 0.75 squared. All right, if you do that calculation, you get 1.06 miles. All right, so that's the answer. That's how far, that's the total displacement. 1.06 miles at an angle of 45 degrees. That's my total vector.